The Wittig reaction is a way of combining a haloalkane and a carbonyl in order to form an alkene. The stereoselectivity of this reaction can be complex at times, and in this video I'm going to try and fully explain all of the different stereoselective outcomes for a Wittig reaction. So first, let's look at the basic reaction mechanism. The first step of the Wittig is the displacement of the halogen by the phosphorus nucleophile. Following this, the base can deprotonate the carbonyl next to the positively charged phosphorus. Here we have generated our species, which will nucleophilically attack our carbonyl group. Key to remember when nucleophilically attacking the carbonyl group is that due to the angle of the orbitals of the double bond between carbon and oxygen, the nucleophile will attack at the Bürgi-Dunitz angle of 107 degrees. Noting that a carbanion will have a trigonal planar geometry, we can represent our nucleophilic attack geometrically as follows. Noting the Bürgi-Dunitz angle here, and exaggerating these to show the effect. We can have the H on this side and the R on this side. Note that excluding a situation where you have a huge R group on the carbanion, you want to keep the R group of the carbonyl on the opposite side to the phosphorus group, which is very large. Alternatively, if we flip our carbanion, we can have this arrangement of the species in space. Now, if we follow these through to the nucleophilic attack, which will usually be an irreversible step for an unstabilized ylid, i.e. where the R group next to the negative charge is not a stabilizing group, this will then be the stereoselective step given that it's irreversible. So if we look at which of these is going to be faster, down in the bottom we have two R groups which is going to cause a steric clash, whereas up here we have the H and the R group covering over a small hydrogen group, so this top step is going to be faster. Therefore, for an unstabilized ylid, our major product will come from this top reaction scheme. So let's work it through and see what we get. Representing the molecule in this planar format, we can see that when we rotate this front group such that the oxygen is able to nucleophilically attack the phosphorus, we will get this intermediate species. However, if we then work through the bottom reaction scheme, we get the opposite. So here, by working through the same way, the bottom example, we see that we get the sterically opposite species ready for elimination. So which of these eliminations will be faster? Well, it will of course be the bottom elimination actually, because we have this steric clash on the top elimination, which when we make these planar is going to be exacerbated. So this top one will react and give us our Z configuration, and the bottom one will give us our E configuration. So what's the major product? As we've already said, the major product for an unstabilized ylid is going to be the top, the Z configuration, despite the fact the final step is slower. And this is because for an unstabilized ylid, the first step in the reaction is irreversible. So the rate of the second step is irrelevant in terms of determining the stereochemistry. It is purely getting to this intermediate, which locks in the stereochemistry. However, for a stabilized ylid, we can get a major E configuration due to the first step becoming reversible if the ylid can be stabilized with the negative carbanion. An example of a stabilized ylid would, for example, be P pH3 connected to the carbanion with a carbonyl group next to it, or an ester group, for example. So this is the way in which we can determine what the stereochemistry of our Wittig reaction product is going to be. If we want to reverse the selectivity of this reaction and get a major product of the E-configured alkene, there is a way we can do this, and that is using the Schlosser reaction, which is a modification of the Wittig reaction in order to get the opposite stereoselectivity, and I will show that in a subsequent video.